Ladies and gentlemen, welcome to our session of the Nečas seminar. And today's speaker is Maor from the Einstein Institute of the Hebrew University of Jerusalem. And got his PhD at the Hebrew University in 2017. And then he spent like almost 3 years or 4 years at the University of Toronto in Canada. And now he is senior lecturer at the Einstein Institute. So his research evolves around elasticity and calculus of variations, and today he will speak about non-Euclidean elasticity.
So thank you, Martin. Thanks to the rest of the organizers for inviting me here. It's a pleasure being back in Prague for many years. As I told Martin, my family is actually from the Czech Republic. My father was born at Teplice many years ago, so it's nice to visit. And as Martin said, I'll talk about part of elasticity theory known as non-Euclidean elasticity that deals with the mechanics of bodies that are pre-stressed, in the sense that they don't have a reference configuration, they don't have a zero stretching mode, if you like. And specifically, I'm going to focus on thin elastic bodies, because somehow this is where most of the interesting phenomena happen. And particularly, I'm going to focus on specific type of thin structures that are ribbons, and I'll talk about shape transitions that happen in them. So the talk will have roughly three parts. The first part, I'm going to introduce the model for non-Euclidean elasticity in general, in the bulk. Then and to motivate it a bit. Then I'm going to focus on thin structures, and then I'm going to present you some work on non-Euclidean ribbons. And the first two parts will be, let's say, will be completely mathematical rigorous, in the sense that there will be theorems that I stand behind them. But the last part is actually work based on work with some experimental physicists, and we have some formal asymptotic theory, but the actual proving it, cleaning up after the physicists, is work in progress. So let's start with non-Euclidean elasticity. So let's start with one slide of elasticity in a nutshell. Like, what do I mean by a very basic elasticity theory? So we have an elastic body and just a domain in Rn, and then we have a configuration into a Euclidean space of the same dimension, and we want to measure how much this configuration stretches the body. So we have some kind of elastic energy this is the hyperelastic assumption that measures that it depends on the local deformation at x. This is the derivative of the function of the configuration, and the energy density measures how much f is far from being an isometry at the point x. And then I sum up over all these. So if I want to measure how much f is far from being an isometry, then my basic assumption would be that the energy density is non-negative and is zero if and only if A is actually or df is actually a rotator. So at each point it roughly measures my distance from rotations. Another typical physical assumption would be frame indifference, that the global rotation doesn't change the energy. Okay? So for the sake of this talk, you can just think that most of the results will work in much larger generality, but you can think about just the energy density being the distance squared from SON. Okay, it's not the most physical thing, but to a leading order, it's the right thing to look at. Okay, but this is a very general model, and then you can do a lot of things with it, but it has a hidden assumption. The hidden assumption is that the assumption that at each point the zero energy mode is exactly the same set of rotations means that you have a global minimizer of zero energy of the functional, no matter what W you choose, as long as it satisfies this condition. Basically, if you have a global rigid motion, it has a zero energy. So it is a reference configuration. And this assumption that you have a reference configuration is somehow very basic. It's what you typically linearize about and so on and so forth. But in many systems, there is no such configuration, even in the absence of external forces or boundary conditions or whatever. So you can ask, where can I find such bodies? And the answer is, maybe the simplest answer is in your kitchen. So this is a carrot field, and I took this picture. I was making a salad or soup, I don't remember, and for some reason I decided not to chop the carrot like this, but and the long side, and then it split like that. And then I was very excited. I ran to the living room. I took my camera. I took a photo. I had to explain to my wife what I'm doing, and. But I was excited because you can see that this is a stressed carrot or a non-Euclidean carrot. Why? Because if it was in its reference configuration, if somebody is in its reference configuration and you cut it and there are no external forces, then it remains in the same shape. But obviously it was like this and now it's split. So it released some stress. So it is a stressed carrot. So the model that I presented in the previous slides doesn't apply to this. So we need a more general model. So here comes non-Euclidean elasticity, and it's basically the same slide as before, only instead of having some domain in Rn with its regular metric, I have a n-dimensional Riemannian manifold with some Riemannian metric. I don't care much about topology in this talk, so you can just think of M as being a domain in Rn with some Riemannian metric on the domain, and the Riemannian metric I'll assume to be smooth. Okay, you can talk about rough metrics, but let's focus on the smooth case here. Now. A configuration is, again, you map this manifold into Euclidean space of the same dimension, and now you want to have an elastic energy. And okay, now the derivative is a map from, at the point x, is a map from the tangent space at point x to Rn. And you want, so your energy density needs to be a function that measures somehow. At each point, it measures how much it stretches at the point x. So it's a function from these linear maps to 0 infinity. And again, the assumption is that you don't that you have zero energy at the point if and only if you are orientation preserving and the map is an orientation preserving and is an isometry. But now, instead of being an isometry between Rn and Rn, I have an isometry between this tangent space with this metric that depends on x and the Euclidean space. Okay, so I denote this by SOG at the point x. So what is an example of such an elastic energy? As before, I want to take the distance squared from this SOG, but you can write it just if you think of G as being just a map from our domain to symmetric, positive definite symmetric matrices, then you can write this in coordinates just as the distance square of df composed with square root of G inverse and SON. Okay, so it's similar to what we had before, only at each point the zero energy mode depends really on x through g. Okay, and now, so this is the same model, and now the basic thing that you want to ask. Okay, okay. So what it measures, basically, you have a Riemannian manifold. This energy minimization, the minimization problem of this energy measures like the question is finding the most isometric immersion of this manifold into Euclidean space of the same dimension, even if you don't have a true isometric immersion. So we want to do the least stretching, the most isometric immersion. So this is minimizing this function. So the basic question is you want to ask is, okay, I have this. I want that if G is curved. So, for example, if we're two-dimensional and MG is basically a hemisphere, and you want to put this hemisphere on this table, then you need to stretch something, right? Then you need to have positive energy. So the basic thing that you want to have is that the infimum of this energy is zero if and only if the curvature of G is zero. Okay? And this is indeed true, and this is an equivalent formulation of this. The infimum is positive if and only if the Riemannian curvature of G is non-flat. This is in the simply connected case when you don't have topological problems. So this is originally and this is a non-trivial question because this energy is non-convex, so you cannot just take a minimizing sequence to zero and work with its limit without saying something. Like the direct methods, the calculus of variations, they don't work as are. You need to do something more. So the original result is Marta Levitska and Muhammad Reza Paxos in 2011, and we generalized this in various ways a couple of years ago. So so we have this this result, but this result is somehow a qualitative result. It tells us that if we have non-zero Riemannian Riemann curvature, then we have positive energy. But how much? Like if you, in some sense, you want to say that if the manifold is curved more, then you have higher energy. Okay. But this is, in general, a very, so this is what's written in red here, finding quantitative lower bounds. And this is, in general, a very difficult problem that we don't have good answers to, surprisingly. But we do have some asymptotics. For example, asymptotics for low energy. For example, one of the key asymptotics is when we treat thin bodies that are almost lower dimensional, and then the elastic energy is rather low, and we can understand somehow how the infimum of their elastic energy depends on the thickness of the body. So this brings us to the second part of the talk, in which I'm going to talk about thin non-Euclidean bodies. So what do I mean again by thin non-Euclidean bodies? These are all, and I'll go through the pictures in a second, these are all three-dimensional bodies, but they're almost lower dimension. So in these three examples, they are very thin, they're almost a surface, they're almost 2D. Okay, so these are plates and shells, if you like. So this is a leaf that it grows faster near the edges of the leaf relative to the inside. So it has somehow too much circumference compared to the radius. So it gets this type of hyperbolic metric that you can see here. This flower is somehow similar. this is a gel made in a lab that was made such that if you put it in an oven, it responds to heat in a non-homogeneous way. It contracts more near the edges than inside. So though you constructed a flat thing, once you put it in the oven, it got some kind of this spherical shape. So these are almost 2D. You have almost 1D, which we call rod theory. Here, this is a plant called, in English, stork's bill, I think. So this is the plant originally, and then when it dries, then it changes the local distances inside. It gets some non-trivial Riemannian metric, and then it gets an interesting shape like this. It helps it actually spread its seeds when it dries up. And our focus today is ribbons, which is something in between. They are very thin, they are very narrow, but they are much more thin than they are narrow. Okay? So they're somewhere in between plate theory and rod theory, and they're, in a sense, they have more things are happening there. And this picture is a plant that is common in the Israeli desert, and it's in Hebrew it's called Chavatzelet HaNegev. In Latin it has a much longer name, but it has, you can see this ribbon-like thing. So let's analyze this. So in order to analyze this, we need to remember a bit of geometry of surfaces in R3. So if we have a surface in R3, so we have a coordinate domain that I call small omega, and we have coordinate map that maps us to a surface in R3. Okay, so this surface is characterized by two things. First, the first fundamental form, the intrinsic metric, which is just, you know, Gij is the derivative of R with respect to I times the derivative of R with respect to J, which measures distances on S. And then the second fundamental form that measures how much the normal changes along S. Okay, and now if you have a configuration, you have, this is your elastic body, and you put it into three-dimensional Euclidean space, then this F, the resulting shape, also has a first and second fundamental form. Okay, so we have the two forms associated with the body and with the configuration, and then an elastic energy, a typical elastic energy, would measure how much, this is Kirchhoff shell theory, it measures how much the body is stretched, how much G bar, the metric of it want to be, differs from GF, the metric of the configuration. This is the stretching part, and then you have a bending part that measures how much their second fundamental form change from one another. Okay? And you have your parameter T that stands for the thickness, and we'll see where it comes from in a second. But note, and this is an important note, that the first and second fundamental forms are not independent. They completely characterize the surface, but they are not independent in the sense that they are related by the Gauss-Kodazzi system. So the Gauss equation tells us that the Gaussian curvature associated with the metric G is the determinant of the second fundamental form. And the Kodazzi system tells us that if we take the covariant derivatives with respect Okay. Do I need to agree to it again, or okay? It's fine. Okay. So while these first and second fundamental form of S are incompatible in R3, they are compatible in some abstract Riemannian manifold. So I can think about S living in some ambient Riemannian manifold. Then I can think about this thin elastic body that is part of this Riemannian manifold. This is our three-dimensional body. Okay, and now we have a three-dimensional Riemannian manifold with a certain metric. Okay, and it can be shown that this elastic energy is nothing but formal asymptotics in the thickness of the elastic energy that we wrote in the that we saw in the first part of the talk. So here it's the yellow one. The yellow body is three-dimensional into 3 dimensions. We put the elastic energy from the previous part of the talk. We take the formal asymptotics as the thickness goes to 0, and we get this. This can be made formal in a sense using gamma convergence techniques. This was first done in some special cases by Schmidt and Levitska and Pakzad, and then in the general case by Kupferman and Solomon, and all of them are based on the famous results of Poetica, James, and Müller regarding plate theory in the Euclidean case. Okay, so but from now on we focus on this energy. Okay, so let us recap. We have a surface with a first and second fundamental form. We have its configuration into 3-dimensional space, and then the first and second fundamental forms of the configuration must satisfy the Gauss-Kodazzi system, and we have elastic energy that is stretching plus bending for each term. But now, you see, look at this energy. GF and the second fundamental form of F, they satisfy some constraints. The G bar and the 2 bar do not satisfy or may not satisfy. So if they don't satisfy, there is no way this energy can be 0, right? For any F, if G bar and the second fundamental form do not satisfy Gauss-Kodazzi, then for any F, for any configuration, the energy is positive. This is the equivalent of having non-zero Riemannian curvature in the bulk case. So now you can ask, can we prove a similar result as before? And the answer is yes. So together with Raz Kupferman and our student Tai Alpern, we proved that the infimum of this energy is indeed 0 if and only if the first and second fundamental form satisfy the compatibility conditions of the Gauss-Kodazzi system. So you can view this theorem in 2 ways. One, you can think about it as a stability result for the Gauss-Kodazzi system. So if you can approximately satisfy the system in this L2 way to any order you can make this as small as possible, then you can actually solve the system. Okay, so this is one way. Another way to think about this is if you're familiar with the Reshetniak rigidity theorem, this is a codimension 1 version of it. And you can ask, okay, I wrote infimum here, then what exactly is the space that I'm working on? And it's basically the largest space on which this energy is defined. So you take W12 functions that whose derivatives have full rank almost everywhere. So the normal is defined. And then you also assume that the normal is in W12, so the second fundamental form is twice integrable. Okay? So this is our second, so this is another kind of rigidity type result. And here are some examples. So if you lost me now, then let's see some examples. Maybe they'll help. Soon there'll be pictures. So the basic, if you just take a page, you take a flat page, okay, then G bar is just the identity, and it doesn't, the normal doesn't want to change, so the second fundamental form is 0. So everything is good. The Gauss equation is satisfied, the Kodatsky equation is satisfied, so the infimmal energy is 0. However, you can take a hemisphere with 0 second fundamental form. This is basically this gel example. Okay, the first fundamental form wants to be a hemisphere, but the second fundamental form wants to be 0. And now the Gauss equation is not satisfied, but the Kodatsky is satisfied, and the infimmal energy by the theorem we just discussed is positive. Now you can have another version of Unfortunately, I have a page of it. Here, the first fundamental form, it wants to be flat, but the second fundamental form, it wants to curve along, say, this way, but unlike what I did here, it wants to have different radii of curvature as you progress in here. And this you cannot accommodate without stretching the paper. Okay? And here indeed, the Gauss equation is satisfied because this has 0 Gaussian curvature and the determinant here is 0, but the Kodatsky equation are not satisfied. Okay, so now a natural question is there a difference between violating Kodatsky and violating the Gauss equation? So the first answer is no, in the sense that if you take t to 0, you always have that the stretching becomes dominant because of this is rather small. So you always have that minimizers or minimizing sequences, they tend to isometries. So GF tends to G bar, and you just pay whatever bending cost you pay among all isometries. Okay? So, and this is regardless of whether you violate Kodatsky or Gauss. But in ribbons, you see much more complex behavior. Okay, so what is a ribbon? A ribbon is a shell, so it has small thickness t, but it's also very narrow. Okay, so we have 2 small scales, t and w, and they're both small, but t is much smaller than w. And we again have a mid-surface, again in red, which has first and second fundamental form, and there is a midline L of this surface. And now we can put, and now there is a configuration of the mid-surface into R3, and we put the same elastic energy as before, only I divided by the volume. Okay, because if W is small, then the volume is very small, so I divide by it. And now you want to ask, what's the behavior as T and W go to 0? But now we have 2 small parameters, so much more things are going on. So here's an example. It's another example where the Gauss equation is violated, but the Kodatsky equation is not violated. This is a body that wants to be, its first fundamental form, it wants to be flat, but its second fundamental form wants to be of a saddle type. Okay, so think about the body that on one hand it wants to be flat, but at every point the normals want to behave like a saddle. Okay, and this is, of course, I cannot do without stretching. And now you can show that in this case the Gaussian curvature, in this case, the optimal way you want to find the optimal solution for a configuration, would have the following first fundamental form. It will look like G, and the only perturbation is in the 1-1 case, and here the first correction would be the Gauss curve is of order y squared. Okay, you have GF of x and y is the identity plus O of y squared, and this first order correction is the Gaussian curvature of GF along the midline. Okay, and now if you write the stretching energy that we had before and just plug in this GF, then you get that your stretching energy behaves like W to the 4th power because of this y squared times the integral of this Gaussian curvature squared plus higher order terms. The bending remains the same. It's the integral of the difference between the second fundamental form times t squared. But now there is the constraint, right? The constraint, the Gauss constraint, tells you that the Gaussian curvature of G and the second fundamental, the Gaussian curvature of GF and the second fundamental form of F are related. The determinant of the second fundamental form is K0. So if you want K0 to be 0, in order to minimize this, then this cannot vanish because the determinant of this guy is non-zero, and vice versa. So they are competing. Okay, but now if there are, so this is just the same thing. This is the energy, the total energy that we wrote, and this is the constraint. So we get that if we have a wide ribbon, so T is much smaller than W squared, then this term is dominant, so we want to make it 0. So K0 is 0, and you get the energy comes from the bending as is, and is roughly T squared from here and lambda squared from here. So this is the energy in the wide ribbon case. In the narrow ribbon case, it's the other way around. This term is dominant, so we want to make this 0, but then you must pay. But then K0 is constrained to be the determinant of this, and therefore it is of order lambda squared. So you have that the energy is of order lambda W to the power 4 and times lambda to the power 4. The bottom line is that you have transition between these regimes. You get different behaviors. Okay, so you actually see such phase transitions in ribbons. So this is what we wanted to understand better, and this is work with the laboratory of Eran Sharon in the physics department at the Hebrew University with a former student and a former postdoc of his. And what do you see here? On the leftmost column, this depicts what the first and second fundamental form want to be, what the G bar and the second fundamental form bar want to be. So in all these examples, G bar is flat. You can see it as the flat surface over this. And the curved thing is how the normal wants to behave. Okay? So the first example is what we've just seen. It wants to be flat, but the normal wants to be a saddle at each point. Okay, so if you're wide, you get a certain shape, and if you're narrow, you get a completely different shape, and there is a shape transition where T equals W squared. And this is, as we'll see next, this is kind of the general case for Gaussian compatibility. Whenever the Gauss equation is not satisfied, then you have a shape transition at T where T is comparable to W squared. However, in all these examples, the other 4 examples, the Gauss equation is satisfied. What is not satisfied is the Kodati equations. And there you see a variety of phenomena. In some cases, you don't see any shape transition. Ignore this. This is just to prove that. This is just to show that what this thing wants to do is like depicted here. This is roughly cutting the carrot again. And in other examples, we see, a shape transition between wide and narrow ribbons, but the powers are, the shape transition are very different. You have t to w cubed or d to w to the fourth. And we wanted somehow to develop a theory so this was seen experimentally, and we wanted to understand this. And so let's do some formal asymptotic analysis. So first of all, we need a good system of coordinates for ribbons, and fortunately there is. You can always find coordinates on your mid-surface that depends on W, such that the metric has this form. It's almost the identity. The only thing that differs from the identity is the 1-1 term, and it looks like 1 times a linear correction that depends on the geodesic curvature of L in S. So in the previous slide, the geodesic curvature in all these 3 examples is 0, but here, for example, is constant. It's constant, okay, and non-zero. And then you have a second order term, which is the Gaussian curvature of S along the midline L, like we had in the previous example, and you have higher order terms depending on the derivatives of the Gaussian curvature. And it can be shown that solving for the optimal configuration order by order, you get a first fundamental form that is of the same type as the reference one, and you don't stretch along the midline. You preserve the geodesic curvature. The first thing that can differ is the Gaussian curvature K0 can differ from K0 naught, and similarly for higher order terms. And now you can, this is the same thing, and now you can just formally write the stretching energy by expanding the Gaussian curvatures in the small parameter y, the width parameter here. And then you get W to the fourth, the difference between the Gaussian curvatures in the midline. This is the same term as from the previous examples. Then W to the sixth with the first order corrections, and so on and so forth. Okay, and you can do the same for the bending term. This is the bending term. This is the second fundamental forms along the midline. These are the derivatives of the second fundamental forms along the midline, and the derivatives, I mean, in the width direction. And each time you take a derivative, you get the W squared term. This is just formal asymptotics. So this is the same energy, and now you need somehow you need to also develop the constraints order by order. Please don't try to read this. It's not very informative. It's just tell you that you can write the Gauss equation and the Kodazzi equations order by order, and then you're just trying to solve this order by order. So let's go back to our example that we had before, right? The first line in the table of examples. So now what the analysis that we did was that K0 vowel 0, this being 0 is inconsistent of the second fundamental form along the midline being the reference second fundamental form, meaning this. So this term and this term are competing, and then we have a transition T equals W squared, because here we have T to the T squared, and here W to the fourth. Okay, but now we can do this also for the Kodazzi case. So let's take, for example, this one. This is the last example that I'll go through. And in this case, so this is the same slide as before, just with a different example. Again, it's the example that the ribbon wants to be flat on one hand, but it wants to bend like this, but in a different radius along, changing linearly along the midline. Okay, so this is this term here. So now you start to analyze. The first term is consistent because kappa naught is 0, but the determinant of the second fundamental form is also 0. So this is fine. You go to the next term. This is also turned out to be fine. Only if you go to the next term, you have inconsistencies. Somehow the first order Kodazzi tells you that the second derivative of this component should be 0, but the Gauss equation tells you that the second derivative of this one term needs not to be 0. And if you trace it back where everything comes from, this is a competition between this term, the second derivative of the Gaussian curvature, and this term, the 0th order term in the second fundamental form. So you have a competition between w to the 8th and t squared. So you have this type of transition, t and w to the 4th. Okay, and this you can do to all these examples, and in some you see that indeed you have shape transitions. In some you see that the competition is between things like, say, this term and this term, but this term is always w to the 4th, for example, is always larger than t squared w squared because t is much smaller than w. And if you have a competition that goes like this, then you have that there is no shape transition. So you get a variety of things with Gaussian with the Kodazzi incompatibilities. So let me sum up what we saw today. So we discussed non-Euclidean ribbons. They're everywhere. There is this plant I showed you before, but there are also macromolecules. So this is super interesting. You have these these chemists are looking on this on some type of molecules that are going. So they are self-assembled macromolecules. They start like long rods, but then they get more material from the solution they're in. But somehow, because of their intrinsic, because of the way the molecules are attached to each other, they don't grow like rods like this, but they grow along a specific surface. So they really become from a rod to a ribbon, and the ribbon becomes wider and wider. And chemists saw that different ribbons look rather differently. So it's very difficult to see here, but some of them really look like this, whereas the wider ones look like this, and they wondered why this is happening, and indeed this theory can give explanation and measurements or predictions on how these molecules behave. And as I said, this last part I presented asymptotic theory for shape transitions. We saw that for Gauss incompatibilities, the result is rather robust. You have a shape transition between t and w squared. But for Kodazzi incompatibility, you have somehow a non-standard shape transition, or you don't have a shape transition. And we can analyze it in kind of a case-by-case thing using these formal asymptotics, but we don't have kind of a general theory. Give me a metric and a second fundamental form that satisfies Gauss equation but doesn't satisfy Kodazzi. I don't have a clear formula that tells you whether there is a shape transition or not, and where. I don't have time for this, but this is seems to be related to some solvability condition of a Monge-Ampere equation, with very non-standard initial conditions. And as I said, all of this part is just asymptotic analysis, and an ongoing project is to work out rigorous results, gamma convergence results, and really prove that this shape transition, even in the Gaussian compatibility case, happens, and actually show that, for example, the infimal energy, if you have Gaussian compatibility, goes like t squared if you're wide, than w to the fourth if you are narrow. So that's the story I wanted to tell you today. So thank you.